So good evening everybody. This is the beginning of everything. And as you can see from the subtitle on the next slide, what I'm talking about is, excuse me, let me just make sure PowerPoint is responding, there we go. I'm talking about a brief description of the origin and the very early history of the universe. How did we go from the Big Bang to get to where we are today with a universe full of galaxies? So we'll start with a look at what the universe looks like right now. Digital Sky Survey, the Sloan Digital Sky Survey, gives us an idea of what the universe looks like. So this might look like an animation, it might look like a simulation, but actually this is more like a 3D atlas, because the positions of various galaxies have been mapped in the sky and their distances measured. So what we have is a 3D map, and this is a fly-through telling us where those galaxies are. And by looking at the distribution of galaxies, we can see that they're not uniformly spread throughout the universe. They seem to be clumped, there seems to be filaments, there seems to be some areas that are essentially empty or void. And so we need to think about how it is the universe came to have that particular structure. We look out into, for instance, the Hubble Deep Field, and we see lots of different types of galaxies, all at different distances, which of course means we're looking back in time to various parts of the early universe, going back a few billion years or perhaps more than 10 billion years. Some galaxies look a little bit blue, some galaxies look a little bit orange, but we have to think about what the evolution of galaxies are, and in particular, where did they all come from? So I'm talking about the creation of the universe. When did it happen? 13.8 billion years ago. How long did it take to make the universe? About 3 minutes, give or take. And where did it happen? Well, that's a little bit of a misconception. You can't talk about the creation of the universe happening at one particular point. The creation of the universe happened everywhere at the same time. Why did it evolve the way it did? Because of the laws of physics. And how do we know that? Well, because of the laws of physics. I'm a physicist, therefore I believe that the laws of physics effectively explain everything. And that's what we're going to be thinking about in this particular talk. Nature in general is not repetitive. The same thing doesn't keep happening over and over again. Might seem that way during lockdown, but generally the same things do not keep repeating. If they did, life would be extremely boring. And similarly, nature is not unpredictable in the sense that if we couldn't figure out what was going to happen next based on our observations of the moment, then it would be impossible to make sense of the world. So nature is actually somewhere in between being repetitive and being unpredictable, which means basically nature is interesting. But we can still ask the question, how does nature work? In other words, what are the rules of the game? What are the rules of the game by which nature operates? If we were looking at that particular collection of objects and we didn't know anything about the game of chess, would it be possible for us to figure out what the rules were simply based on that snapshot? There's a few different pieces of all different shapes. They appear to be two different colours. So perhaps this is a game between two people. But trying to figure out what are the allowable moves for each piece would be very difficult just looking at that snapshot. And similarly, if we simply look at a galaxy and say, right, that's a collection of stars, what's going on there? How is it evolving? How did it come to be? How did we get to that from the Big Bang or from 13.8 billion years ago? Again, that snapshot doesn't tell us what's going on. What we would really like to do is to sit and watch that galaxy, in much the same way that it would be far better to have a video of somebody playing the game of chess for us to work out what the rules are. It would be far better to have a video of the galaxy and watch it evolve, watch it rotate. But of course it takes hundreds of millions of years for a galaxy to rotate, and we haven't got that long. So what can we do? Instead of thinking about a single snapshot of a single game, if we aren't allowed to take a video of the game in progress, then one option is to look at 1 million different games all at various stages of being played. And in a sense, that's what's happening when we look at a single galaxy. We don't get the full picture, but if we look at the Hubble Deep Field, then we're looking at thousands of galaxies. And if we look in other telescopic fields, we can see millions of galaxies, each of which is at a different stage of its evolution. So we can get an idea of the rules of the game, not by concentrating on one galaxy, but by looking at as many as possible, each of which is a little snapshot of its own back in time. But isn't the universe just too complex to figure out what the rules of the game are? We look at a little bit of our local backyard. Perhaps you recognise this as part of the Orion constellation, the Great Nebula off to the right, the Horsehead Nebula down in the bottom left. But surely that's just far too complex to be able to figure out what must the rules of the game be in order to produce anything that's as complex as that image, let alone the rest of the universe. Well, by analogy, we can say, surely the mathematics that's required to produce this particular collection of pixels, surely that must be a very elaborate, a very complex piece of mathematics. What equation possibly produced this particular collection of pixels? In fact, if we zoom in and look at one particular part of this pattern and keep zooming in, we find it's even more complex than we can see simply from one pixel on one screen. If we zoom into this particular pattern, we find the detail just keeps on coming and keeps on coming. And yet this entire set of mathematical points, some of you might know it, it's the Mandelbrot set, the entire collection of points can be generated from one mathematical formula. But we can ask ourselves, if we weren't already aware of this particular phenomenon, we can look at this and say, well, surely it must be a very complex equation, because the more we zoom in, the more detail we see. Occasionally we see a motif that looks a little bit similar. That sort of object that looks like a seahorse head seems to crop up more than once, but it's never actually repeating. There's a similar sort of motif, but if we keep zooming in, we keep seeing more detail. And all of the pixels in the image you can see and in the video inset are all generated by one formula. And surely we can say to ourselves, that must be so complex, it's almost beyond comprehension how complicated that maths must be in order to generate all of the coloured pixels that we see here in this particular animation. And yet, when we actually look at the mathematics, we realise that the mathematics, the rules of the game, if you like, for this particular set of coloured pixels, not just what we see in front of us, but the entire, if we were to zoom in 1,000-fold, 1,000,000-fold, if we zoomed in 1,000,000,000-fold, we would see all that detail, and it all comes from that formula. Z equals Z squared plus C. We don't have to worry about how, but that formula is all you need to generate the entirety of the Mandelbrot set. So just because something looks extremely complex does not mean that the underlying rules of the game are beyond our comprehension. Einstein summed this up quite nicely. One of the most incomprehensible things about the world, or the universe if you prefer, is that it is comprehensible. Just because it looks very complex does not mean it's beyond our understanding to figure out why it looks the way it does. So let's have a think about the flow of thought that gets us to understand the universe. We observe galaxies moving away from each other. That was known something of order a century or so ago. And from that we conclude that the universe is expanding. And if we wind the clock back, that would imply that the universe was a lot smaller in the past. As well as looking out, we can also look in, and we can do laboratory experiments. For instance, we can bang particles together to get an idea of what matter is made of. We can get an idea that molecules are made of atoms, and atoms are made of smaller fundamental particles, and particle physics is about trying to understand what that structure is. So at the Large Hadron Collider, the LHC, protons are being fired into each other to see effectively what comes out. And by a combination of looking at the universe and looking at how matter is put together, we hope to be able to understand how the universe works. But along the way, we have to make some assumptions. And one of the assumptions is that the laws of physics at one place are the same as the laws of physics at another place. If we have to keep changing the underlying rules of the game, depending on where we are, we'll make no progress. If I assume that the laws of physics that apply to me are not the same as the laws of physics that apply to you, or to apply to somebody in Australia, or applies also on Jupiter, or Alpha Centauri, or the Andromeda Galaxy, or somewhere else, then we can't make progress. And similarly, we have to assume that the laws of physics now are the same as the laws of physics at some other time. In other words, if it was actually the case that the laws of physics kept changing, and the laws of physics as I understand them today would be completely different tomorrow, or next year, or the year after, then again, I can't make any progress in understanding the universe if somebody keeps moving the goalposts. So we have to assume that the laws of physics are immutable. They're the same everywhere, and they're the same as a function of time. Then we can make some progress. And by observing the universe and observing some Earth-based experiments, we can start to draw conclusions. And we conclude that the universe was born in a very hot, dense state, we call it the Big Bang, 13.8 billion years ago, and has been expanding and cooling ever since. So the big question is, where did all the matter we see today come from? We look out into the universe, and within the observable universe, which is something of order 100 billion light years across, we see 1 trillion galaxies which contain hundreds of billions of stars and a whole load of gas and a whole load of dust. Where did all of that mass that we see come from? And we can ask ourselves the question, well, if we think it came from a Big Bang, how far back in time can we go towards that Big Bang before we say, well, we don't really understand whether the laws of physics that we think we understand actually still apply? Of the first 13.8 billion years of history, i.e. from zero up to now, how far back can we go? Are we happy to go back 12.8 billion years to the first 1 billion years of creation? Yes, no problem. What, can we go back to the first million years after the Big Bang? Yes. What if we go back to the first 1,000 years? Yep, no problem. The first year? Yep, as far as we know, if we go back to the first year out of those 13.8 billion years, we're still in a region where we think the laws of physics are as we understand them here and now. What about the first day? What about the first hour? Yes, we're still on solid ground. What about the first minute? What about the first second? Yes, as far as we know, we're still on solid ground 1 second after the Big Bang. What if we go back to the first millisecond after the start of the universe? Yep, as far as we know, still okay. The first microsecond, what about the first millionth of a second? Yep, as far as we know, everything is still fine. The first nanosecond? Yep. The first picosecond, what about the first trillionth of a second after the Big Bang? Now we're not too sure. That is the point at which we have to put our hands on our hearts and say, I'm not actually sure what happened any earlier than 1 trillionth of a second after the Big Bang. Everything from that point onwards, we think we've got a good handle on, for reasons that I'll come to shortly. But that first picosecond is still a little bit of a mystery. But we can clearly go back a long way through that 13.8 billion years. So that was a rather lengthy introduction to set the scene for what I'm calling, how do we work out what the laws of physics are? How do we work out what the rules of the game are, using our understanding of what the universe looks like and our understanding of how matter is put together. I'm going to start from now on with just a couple of basic ideas, and then we're going to look at what happened in the first fraction of a second after the Big Bang. Then we'll look at the first few seconds. Then we'll look at the first few minutes. Then we'll have to change gear slightly, or we'll be here all night. And then we'll fast forward the next 377,000 years. That's not a random number. There's a very specific reason why we're jumping ahead to that point in time. And then we'll zoom through the next 13.8 billion years in no time at all. So that's what we're going to cover. Firstly, a few basic ideas. Some of these you'll know, some might be new to you. We are all made of atoms. That's probably not news to any of you. And an atom is a positively charged nucleus and a whole load of negatively charged electrons buzzing around like bees in a beehive. So if we wished, we could take an atom and we could separate it out into a nucleus and electrons. We could take those positively and negatively charged particles, and if we put in enough energy, we can separate them out. In other words, we can split the atom. Electrons, as far as we know, are fundamental particles. They exist, and you can't cut an electron in half and see what's inside. As far as we know, there is no inside. It is just a fundamental particle. Whereas a nucleus is made of smaller stuff. We could take a nucleus and, given enough energy, we could break it apart and see what it's made of, and we find it's made of protons and neutrons. We don't have to worry too much about understanding the particle physics at this stage of what is a proton and what is a neutron. We're just going to accept that a nucleus is made of different types of particles, and we're going to call them protons and neutrons. And protons and neutrons themselves are not fundamental particles, in that if we provide them with enough energy, we can take a proton and find out that inside a proton it's actually made of smaller stuff. It's made of 3 particles, which we call quarks. Again, we don't have to worry about what are the properties of these quarks. All we have to worry about is the fact that they are fundamental particles which, as far as we know, you cannot take a quark and cut it in half and reveal its contents, as it were. So there's a group of fundamental particles. We happen to call them quarks. Bit of a funny word, but that's what they're called. And 3 of them make up a proton, as it happens. 3 of them make up a neutron as well, but I'm just trying to indicate that we have this hierarchy of structures. If we put in enough energy, we can tear an atom apart. If we put in more energy, we can tear a nucleus apart. If we put in even more energy, we can look inside a proton. So there's an implicit energy scale here. I've been talking about what's inside each of these, like a Russian doll, but really this is an energy scale because it takes more and more energy to break down matter into these various stages. But as far as a physicist is concerned, low energy means low temperature and high energy means high temperature, in terms of if we have a soup of particles and we want to work out how much energy each particle has, well, that depends on the temperature of the soup, if you like. So we know, remember, that the universe started hot and is cooling down. So if it started hot and is cooling down, and low temperature is cold and high temperature is hot, that means time is running upwards, because we start from a hot universe and the universe is cooling down. What that means is the universe was made from the bottom up. In the early universe, for instance, if we had quarks, we couldn't expect those quarks to make a proton, because in the very early universe there was simply too much energy, and if you have a very energetic particle, it will simply break down to its constituent parts. But eventually there will have come a time when the universe has expanded enough and cooled enough such that it'll be cold enough for quarks to make a proton. But it would still be too hot for protons to make a nucleus, because if you try and put protons and neutrons together to make a nucleus, there would be simply too much energy floating around and the nucleus would break apart into its constituent parts. But eventually there will come a time when the universe is cold enough for a nucleus to form. And similarly, at that point it'll be too hot for atoms to form, because at that point there'll be so much energy around. If you try and put a nucleus and electrons together, there'll be so much energy the atom will simply tear itself apart. But eventually there will come a time when the universe is cold enough for atoms to form. So that's what I mean by the universe is built from the bottom up. Because the universe is cooling, and because each of these stages needs more and more energy, that means particles make protons, and then protons make nuclei, and then nuclei make atoms, and eventually atoms make us. And that's the order in which the universe builds things. Okay. Oops, there we go. So let's start the journey from t equals 0. Remember, we haven't yet got to the point where we absolutely or reasonably know what's going on. At t equals 0, what happened at the instant of creation? Well, perhaps no surprise, science cannot as yet provide a definitive answer to what happened at t equals 0. We believe perhaps it was a quantum fluctuation in which energy, and therefore matter, was borrowed from nothing. Now that sounds a bit like a cheat, and it certainly sounds really weird that you can borrow as much energy or mass as you like from nothing. It doesn't have to come from somewhere. Now, yes, that goes completely against common sense, and it sounds really weird, but quantum mechanics is weird. Quantum mechanics is the framework we have for describing things on a very small scale. And a quantum fluctuation is simply a jump or a change in nothing that suddenly produces something like a couple of particles or something like that. So it's a bit of a leap of the imagination to say the entire universe can simply be a fluctuation in nothing which suddenly comes into existence, but that doesn't fly in the face of quantum mechanics as far as we understand it. So the real question, I guess, is how big can the fluctuation be? How much energy can you borrow from the bank of nothing, as it were? Well, there is a fundamental limit according to our understanding of quantum mechanics. The amount of energy you borrow times the time that you borrow it for does have an upper limit. In other words, if you wish, you can borrow a lot of energy as long as you pay it back very quickly, or if you are only borrowing a small amount of energy, you can borrow it for a much longer length of time. Pretty much the same as borrowing money from the bank. If you borrow £1 from the bank, the interest rates are probably not high enough for you to worry too much about accruing some interest, and it'll be a long time perhaps before you pay it back. But if you borrow £1 million with the same interest rate, you'll be very keen to pay back that loan as quickly as possible. And the argument here with the physics is you can borrow energy from nothing as long as you pay it back before the universe has time to notice that you've borrowed it. So the key thing in terms of how long could we possibly borrow energy is how much energy are we borrowing? And the weird answer is when you look around and you say, well, how much energy is there out there? There's a huge amount of mass that we see, and we can work out the energy from E equals mc squared, so we get a large amount of positive energy based on all the mass that's out there. But when we look at the gravitational energy of every star to every planet, or every particle to every other particle, every galaxy to every other galaxy, when we work out all of the gravitational energy, which happens to be negative, and we add it to all the mass energy, which happens to be positive, the answer is the total energy of the universe is roughly 0. So if the total energy is 0, then the time we have to pay back the loan looks like it could be as long as we like. So that might sound like a total and utter fudge, and yes, we haven't got a totally satisfactory explanation, but that might be the answer to why the universe came into existence in the first place. Let's jump forward, and we're going to jump forward by the unimaginably small time interval of 10 to the minus 35 seconds. By that time, the universe has expanded until it's about the size of a golf ball. And by the universe, I mean what we currently say is inside the observable universe. We have no idea what's happening outside that. So everything that is currently inside the observable universe, something of order 100 billion light years across, everything that's now inside that volume was in a much smaller volume at this particular point in time. So in other words, you could say the observable universe was about the size of a golf ball, with a little bit of artistic license. So, of course, it was very dense. If everything that we currently see in the observable universe used to be only a few centimetres across, then clearly it was a very, very dense state, to the point where the numbers are almost meaningless. But one thing that we bear in mind at this very early stage was the universe was very small, yes, and just like a golf ball, it wasn't perfectly smooth. So the golf ball has dimples in it. I'm not saying the universe has dimples, but it did have variations in density and temperature. In other words, the sphere that we're talking about that contains what we now call the observable universe, it wasn't perfectly uniform. There were variations in density and temperature back at that early stage. Much later, when the golf ball has expanded and the universe has expanded to much larger scales, then those small variations in density that were in the golf ball, they eventually became the structures that we see today that we call galaxies and clusters of galaxies and superclusters of galaxies. The density variations in the first place eventually became the density variations that we call galaxies. But we'll see that happening. Let's not get ahead of ourselves in the timeline. We'll see that a little later on. Now we jump forward to 1 picosecond, 10 to the minus 12 seconds, 1 trillionth of a second. The universe has expanded from a golf ball until it's the size of something of order the solar system. Okay, the solar system doesn't exist yet, but just to give you an idea of scale, something that is not yet light years across. The temperature has fallen. Remember, as the universe expands, it cools, and the temperature has fallen to about 10 to the 15 Kelvin. And this is a particularly important point because the energy of all of the particles in the universe, which we refer to as a quark soup, it's a soup of fundamental particles. Energy was borrowed from nothing. Energy can be converted into the mass of various particles, and it's going to be a whole load of fundamental particles, quarks and other things, but still people often refer to it as a quark soup. Perhaps we should be calling it the quark and electron and other fundamental particle soup, but it's not quite as catchy. But the point is, the energy of each of the particles in this soup is, roughly speaking, the energy that we can reproduce by banging particles together in the Large Hadron Collider. In other words, from this point onwards, we can actually test any ideas we have about what the early universe was doing, because from this point onwards, the energies involved are accessible by doing experiments in particle accelerators on the Earth. That's why I said early on that from 1 picosecond onwards, from temperatures of 10 to the 15 Kelvin downwards, from this point onwards, we can test our ideas. We can have a hypothesis, we can test them by giving particles the same amount of energy as we're talking about here. Prior to a picosecond, we can't do that. We can't access the sort of energies we're talking about prior to 1 picosecond after the Big Bang. So we borrowed energy, and energy can be converted into matter, back and forth and back and forth. Energy can create matter and antimatter. Antimatter is simply the mirror image of matter. So for instance, if we think of matter as being, let's say, an electron has a mirror particle called an anti-electron. It pretty much looks like the same thing. It has the opposite electrical charge. An electron is negatively charged, an anti-electron has the same mass but is positively charged. So energy can create matter and antimatter and matter can annihilate to produce energy. And this exchange is going on back and forth and back and forth. Matter and antimatter are made in equal amounts. Every time energy is converted into matter, we get an equal amount of antimatter. So I don't know how to represent energy, so I'm just going to use a big capital E here to represent some amount of energy. And on ridiculously fast timescales, energy can be converted into matter and antimatter. Probably not an orange and an anti-orange, but it doesn't actually matter whether we're talking about making quarks and antiquarks or making electrons and anti-electrons. The point is, it makes something and it's anti-something. That's all we need to worry about. And having made that little piece of matter and antimatter, very quickly they will annihilate with each other and then produce energy. And that energy can then go on to produce another piece of matter and antimatter. Not necessarily the same orange and anti-orange. It could produce probably not a hot dog and an anti-hot dog. It doesn't matter. It'll just produce something else and its antimatter equivalent of that something. And that will be going on backwards and forwards, many, 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 many times per second. And for a reason that I'll come back to right at the end of the talk, there's something we don't understand here. Somehow matter gained a very small excess over antimatter. Originally, the same amount of matter and antimatter were made, exactly the same amounts, but somehow they got slightly out of balance for reasons we don't fully understand. And what that means is if we make a whole load of matter and a whole load of antimatter, but not quite the same amount of each, then you can see that on the left, the orange and its anti-equivalent can annihilate to form some energy, and similarly for the second orange and the third orange and the fourth orange, but the last orange is left over. So most of that collection of matter and antimatter can annihilate with their opposite, their mirror partners as it were, to produce energy, usually in the form of light, electromagnetic radiation. But one orange at the end there doesn't have any antimatter to annihilate with, so that is left over. In other words, what we have in the universe is a whole load of radiation, a whole load of light flying around, and we have a little bit of matter. And that little bit of matter is you, me, the Earth, the Sun, the Milky Way. Every galaxy we see in the observable universe is made of that little bit that was left over when some amount of matter didn't have an equivalent amount of antimatter to annihilate with. The excess was not 1 part in 10, which is sort of what I've indicated in this little graphic here. For the point of illustration, I've shown a 10% excess. It's not actually 1 in 10, the imbalance. The imbalance is closer to 1 part in a billion. So it's only a tiny amount that's left over. So you could say there's a billion photons of light for every particle of matter. But we are very grateful because those particles of matter are precisely what make up everything that we see in terms of the matter around us. Let's move ahead to a millisecond or so into the time after the Big Bang. Matter and antimatter are continuing to be popping into and out of existence, swapping energy to matter and antimatter, back to energy, back and forth, back and forth. Protons and neutrons are made out of quarks. So quarks are fundamental particles that were presumably born in the Big Bang. We have no reason to assume otherwise, because as far as we can tell, quarks don't have any substructure. So the quarks that were made in the Big Bang eventually get together when the temperature is low enough, after a millisecond or so, to make protons and neutrons. So we're not going to turn this into a lesson in nuclear physics, but basically a proton is simply the name we give for a bag of 3 quarks on the left-hand side. And a neutron is the name we give to a bag of 3 different quarks. So we don't need to worry about why, but it just so happens that when quarks get together in 3s, a particular combination of quarks is what we call a proton, and a different combination of quarks is what we call a neutron. We're not going to worry about why they're coloured red, green and blue, and we're not going to worry about why some of them are labelled U and some of them are labelled D. That's actually shorthand for up and down, but we don't need to worry about why we use those labels, but you might have heard those labels used in some context. Quarks can change into each other quite readily at this temperature, and therefore protons are turning into neutrons and neutrons are turning into protons, back and forth, because everything is in a state of flux at this particular temperature. But eventually, let's say after about a second or so, the temperature has dropped somewhat. The temperature is now only about 1 billion Kelvin compared to the very high temperatures we had earlier. And remember what I said early on about the idea of the Russian doll series? As the universe cools, then it's no longer possible for things to jump backwards and forwards. Given enough energy, it's easy for protons and neutrons to swap backwards and forwards. But as the universe is cooling, there's now no longer enough energy for that to happen very readily. Now it just so happens protons are a little bit lighter than neutrons. They're very similar in many respects. But protons are charged, but most importantly, the protons are lighter than neutrons. There's only about 1 part in 1,000 difference, only 0.1%, but that does make a difference, because the universe is making shed loads of protons and shed loads of neutrons, but because there's a slight mass difference between them, the universe makes more protons than it does neutrons, and this is fundamentally very important. Why does the universe favour the lighter of the two particles? Well, there's a sort of general rule that nature always favours the lower energy state. If you take a ball and you take it close to the top of a hill and let it go, it will roll downhill into the valley. It won't roll uphill. Uphill, the top of a mountain is a high energy state, the bottom of a valley is a low energy state as far as gravity is concerned. So a ball on a slope will move towards the lowest energy state, the bottom of the hill. And by saying that nature always favours the lowest energy, because E equals mc squared, effectively we can say that nature always favours the lower mass. So they're only slightly different, which is why you don't get all of the universe made of protons and none of them made of neutrons. We do make some neutrons because the masses are similar. They're 1 part in 1,000 different. And if we move forward from seconds to a couple, 2 or 3 minutes or so, well, neutrons are unstable and some of them decay into protons. We know that because we can simply watch them. In the laboratory, if you were to take one neutron and take it away from a lot of its neighbours and simply put it in the middle of nowhere and watch it, after 10 minutes or so that neutron will change into a proton. So we know that neutrons are unstable. So that means the ratio of protons to neutrons changes slightly. Rather than 3/4 protons and 1/4 neutrons, we've now got a ratio out of the 16 that I've chosen just as illustration. Now 14 of them are protons in red there, and 2 of them are neutrons. And from that we can draw a very important conclusion. Now that the universe has been going for about 2 or 3 minutes, it's cooled down to the point of 100 million Kelvin or so. It's now cold enough for protons and neutrons to start getting together. Up until now, the universe has been too hot for nuclei to form. They would be ripped apart as soon as you try and put them together. But at this point, after 2 or 3 minutes, the universe is cold enough that you can take protons and neutrons and put them together and start to make nuclei. And one of the most stable structures you can get with protons and neutrons is if you take 2 protons and glue them to 2 neutrons, you get a very stable structure. We usually call that structure the nucleus of a helium atom. Sometimes we might call it an alpha particle. But we know from experiments we do in the laboratory that 2 protons and 2 neutrons are very stable, and that's what they would like to form. So of the 16 particles that we've got there, 2 protons are going to marry up to 2 neutrons and make a nucleus of a helium atom. But that leaves us with 12 bachelors. They haven't got any neutrons. Remember, they outnumber the neutrons by the ratio of 14 to 2. So some of the protons are lucky enough to marry up to the neutrons and they make a helium nucleus, and then we're left with 12 bachelors, which are simply lone protons. And I've labelled them there nuclei of hydrogen because 1 proton is simply the nucleus of a hydrogen atom. So the point is that after 2 or 3 minutes, let's say 3 minutes, after 3 minutes the relative abundance of hydrogen and helium has now been decided. From now on you can't turn protons into neutrons or neutrons into protons, and you can't make anything else. These structures are effectively now set in stone. The universe is too cold to start changing what we've got at this point. So this is a prediction of the Big Bang Theory, that after 3 minutes all of the hydrogen and helium in the universe were made, and they should have been made in those ratios because that's what we've got from our understanding of the laws of physics. The rules of the game say that if we've got this right, when we look into the universe, we should find a certain amount of helium and a certain amount of hydrogen. In terms of mass ratios, just count the circles, there should be 75% of the universe should be made of hydrogen and 25% of the universe should be made of helium, to the nearest percent or so. And that is what we actually observe. When we look out into the universe, if we ignore for the moment the fact that some stars are converting hydrogen into helium, that's actually quite a small effect. If we look at the gas that's out there, we find that of all the gas we see, 3/4 of it is hydrogen, 1/4 of it is helium. Precisely what we would expect from the ratio that comes out of this calculation. That is what gives us confidence that we think we've got the rules of the game right, because that's a prediction which we can test by observation. If the theory says that it ought to be this ratio, but when we look we find a completely different ratio, that means our theory is wrong and we have to throw it away and come up with something else. But it works, it fits, and so we think we've got it right. We now jump ahead 377,000 years, simply because nothing much interesting happens after those 3 minutes. It takes 3 minutes to make all the hydrogen and all the helium, and after that nothing much happens. The universe, of course, continues to expand and it continues to cool. And 377,000 years is a particular point because that is the point at which the universe is thought to have cooled to about 3,000 Kelvin. Why is that an important number as far as we're concerned? Well, that is the temperature that allows atoms to form. As long as you're colder than about 3,000 Kelvin, it's possible for a nucleus to hang on to some electrons. If you take any constituent matter and heat it up way above 3,000 Kelvin, then you don't have atoms because the electrons are simply ripped off those atoms and you end up with free-floating nuclei and electrons in a so-called plasma. You have the charged particles floating around in a sea rather than a positive nucleus with negative electrons buzzing around it. So at this particular point, 377,000 years after the Big Bang, that's the first time that atoms can exist. So the universe at this point changes from a plasma of charged particles to a collection of neutrally charged atoms. And for the first time, the universe becomes transparent. Up to this point, it was an opaque plasma through which light couldn't travel without interacting with one of the positive or negative charges. But from this point onwards, the universe becomes transparent, and so light that was previously trapped in the plasma is now free to fly across the universe as it wishes. And that light is sometimes referred to as an echo of the Big Bang. It's not really an echo, but it's a sort of a ghost, if you like, because for the first 377,000 years, the light of the material, the matter, the energy inside this large fireball couldn't be released. But at this point, we see the light, because the light is now free to fly around the universe. At the time, the universe would have been white hot. 3,000 Kelvin, if you take an object and heat it up to thousands of degrees, it will glow red hot after a few hundred degrees, and when you've got it up to a few thousand degrees, it will be glowing white hot. So you might think that it should be visible light. Why do we not see visible light from the Big Bang? Simply because the universe has now expanded and is much bigger than it was when the light was released. The universe is now about 1,000 times bigger than when the light was released after 377,000 years. So the light that would have had a wavelength around about the visible wavelength, microns or so, it's now been stretched 1,000-fold. So instead of having a wavelength of order microns, that light now has a wavelength of order millimeters. In other words, that light is not seen as visible light, it's seen as microwaves, simply because that's what happens if you take light and stretch it 1,000-fold. And that is the origin of the cosmic microwave background. That is why the discovery of the cosmic microwave background was so important. It was effectively a nail in the coffin of any theory other than the one that says the universe was born in a Big Bang, because you can't explain the cosmic microwave background unless you start with a Big Bang and then after a certain length of time the universe becomes transparent and then you see the microwaves. So it's not perfectly smooth. When we look, this is an all-sky picture of the microwave background. It's not perfectly smooth in that there are some areas that are just a little bit hotter than other areas, some areas that are just slightly higher intensity microwaves than other areas. And that is simply because, remember, the golf ball was not perfectly uniform, it was dimpled. It's got variations in density and variations in temperature. And even though it's expanded a long way from being the size of a golf ball, those dimples, if you like, are still visible. Those variations in temperature and density are imprinted into the cosmic microwave background. And that is precisely why people are observing very closely what that cosmic microwave background looks like. Yes, it's very smooth, but those small variations tell us about the early universe. And that's why satellites, it's difficult to see these microwaves from the ground, so satellites are being used to observe the cosmic microwave background in ever greater detail to try and improve our understanding of the very early universe. If we have a look at what happens to these dimples, if we go back beyond the cosmic microwave background to further into the future, if we think about the variations, here we're taking simply a small section of the entire chunk of the universe. We've taken a cube, if you like, and said, well, let's assume it's full of matter, but not totally uniformly dense. Let's take a cube full of matter and let's just vary the density ever so slightly at random in various points. So this point might be slightly more dense than average, this point might be slightly less dense than average. Let's take that, and in a computer simulation, let's see what would happen if we then let gravity do its stuff. And we find the densest regions become even denser, and the regions start to change into a structure which we can describe as a cosmic web. We see these filaments of matter, and occasionally we see voids that appear to be empty, and you can see that matter is flowing down the filaments and collecting into these regions where filaments knot together. And this is precisely where galaxies and clusters of galaxies and superclusters of galaxies are forming. That's where the matter is at its densest, when you let gravity do its stuff over a volume in which you start with slight changes in density. Gravity, in a sense, exaggerates those to the point then we then get large regions which are almost empty and small regions which are now very dense, and this is where stars and galaxies will be forming. And there's lots of these simulations out there. At the bottom there I've just given you a web link. If you wish to go to the Illustris project, the so-called TNG project, you will find lots of videos that show you how the universe has evolved from the very early days to the sort of structures that we see around us at the moment. So if we look at our immediate local neighbourhood, there's the Milky Way marked in red there. You can see the Andromeda galaxy on the right, and there's a few satellite galaxies peppered around us. Most of them are quite small. If we look at a somewhat larger scale, let's go out further afield. Our local galactic group is now written in red there near the middle, and we can see that there are various clusters of galaxies. They're not uniformly distributed. We see there's quite a large cluster over there on the right, the Virgo cluster. There's another one further down in the lower left, the Fornax cluster, and we can see there's not much in the top left, not much at the bottom, but there's almost a hint now of a filament indicating there's a line there of various galaxies and clusters of galaxies and superclusters. And if we go out on another larger scale, we can start to see the universe is starting to look a little more uniform, but again we can see that we have filaments, and we can see on the right hand side there, the Boutet's void, for instance, is labelled just on the right. This is a reminder that what we're effectively looking at are variations that have been produced by the dimples in the golf ball. Some regions are underdense, some regions are overdense, so we have a lot of galaxies over here and we have a void over there. It's the result of of gravitation collapsing the original density variations so as to produce the galaxies and the superclusters of galaxies that we see around us. So on the largest of scales, we say the universe looks the same everywhere. in the sense that if we look on a large scale, the foamy or filamentary or the cosmic web structure of the universe looks the same in the sense that the top right-hand corner looks pretty much the same as the bottom left-hand corner, which looks pretty much the same as the top left-hand corner. If we were to start to zoom in to particular regions, we find that we get more and more detail in these filaments, and we see where the filaments intersect, we get the galaxies. And that's shown in this simulation. This particular simulation is called the Millennium Simulation, where we go from the foamy structure of the large-scale universe on a spatial scale of order billions of light years. If we zoom in to the filamentary structure, we zoom into the cosmic web. Here we're going to one particular cluster, and we can see now we've got clearly a couple of filaments that appear to be intersecting. Maybe there's more than two filaments intersecting. Matter fell or flowed down these filaments and started pooling in this particular area, and that over concentration of matter is where we started to get star formation, where we started to get galaxies forming. We're now zooming into the point where we're now looking on scales not of billions of light years, we're now looking at scales of order millions of light years. We're now looking at the universe on a scale more like the scale of galaxies. And if we zoom back out, we can remind ourselves that that particular galaxy cluster is just one of billions of similar galaxy clusters, and on a large enough scale, the universe starts to look foamy but relatively uniform. So what about the next 13.8 billion years? The bottom line is, as long as we understand where hydrogen atoms come from, in other words, you could say, if you wish, as long as we understand the first 3 minutes, as long as we understand the first 3 minutes generates a shed load of hydrogen, then if we start with a universe full of hydrogen, then we've got an idea of galaxies which are full of stars, so we understand stars and galaxies, and we can understand the processes that lead to planets and trees and mountains and snowflakes and rainbows and cats and... Okay, perhaps not cats, because I don't think anybody really understands cats, but if we start with a shed load of hydrogen, then we can start to understand how that hydrogen can form stars, how stars ignite, how stars form galaxies, and everything that comes after that. Yes, I admit I'm papering over a lot of cracks, and there are still some details of evolution to be worked out, and the whole process of how do we go from the cosmic web to spiral galaxies, for instance, is quite an interesting story, but it's not one that I have time to cover here. So yes, the evolution of galaxies and the evolution of stars is indeed interesting, but you could argue that as long as we start with enough hydrogen, then we are basically in the position to make pretty much anything we like. So here's a graphical reminder of the timeline of what I've been talking about. We're not too sure what happened in the extreme left of the picture, but we believe that the universe existed in a very hot and very dense state in the very early universe, and was basically a soup of fundamental particles, quarks and electrons, and probably other particles, but let's just call it a quark soup in this context. After a fraction of a second, those quarks eventually were cold enough that they could form little bags of 3, which we then label protons and neutrons. And after 2 or 3 minutes, those protons and neutrons can get together to form the nuclei of helium, and any protons that are left over simply become the nuclei of hydrogen. If we wait 377,000 years, the universe is then cold enough for atoms to form. In other words, the hydrogen and helium nuclei can grab hold some of the electrons that are floating around and actually form atoms. The universe becomes transparent, the light is released, and we see that light as the microwave background. Nothing happens for a little while because it takes a little while for hydrogen to make stars. After the cosmic microwave background has been generated, or released if you like, there might be a few million years or so before the first stars start to switch on. Gravity does its stuff, starts compressing hydrogen clouds down to more dense regions in which fusion can take place, and the first stars are ignited. Up to that point, we would call it the Dark Ages, because the universe didn't have any stars for a little while, and then stars came online, and then we get to the point we now understand of stars and galaxies, which I've labelled the now point, 13.8 billion years later. So yes, there are still some problems. The jigsaw is not complete, and the main outstanding questions are: why did matter win over antimatter? We are eternally grateful that it did, because if they stayed in balance, the universe would be full of radiation and there would be no matter left over once all of the matter had annihilated with an equal and opposite amount of antimatter. So what actually nudged the asymmetry? What actually pushed it in the direction of the imbalance? And why is the imbalance 1 part in a billion rather than any other number? And I've been talking about everything we can see in the observable universe. I've been talking about looking out into the universe and seeing stars and seeing galaxies, and we know that galaxies have got a lot of dust and gas in them as well as stars, so we know there's an awful lot of stuff out there. But what about dark matter, which I haven't mentioned up to this point? We think that galaxies are, and presumably other regions of space, are full of this enigmatic dark matter that seems to be causing galaxies to rotate at the wrong speeds and holding galaxy clusters together where you wouldn't expect them. So what is the nature of this dark matter? Presumably it was born in the Big Bang, but what is it? Is it astronomical objects, or is it a particle that we haven't detected yet? Are we missing something? We are made of quarks and electrons and very little else, but maybe dark matter is some particle that we are completely and utterly missing because we haven't been looking in the right place to understand what this particle is. And even more enigmatically, what is dark energy? Because the universe is expanding, and we might expect the universe to expand, and then gravity will be pulling all objects towards all the other objects, so surely the expansion ought to be slowing down. And indeed it was for a few billion years, but now it looks like, most recently, the expansion of the universe appears to have been accelerating. It's as if something is pushing the galaxies apart. There's a sort of anti-gravity out there. Where did that come from, and what is it doing, and why? So we have some fairly fundamental big problems with understanding some of these elements. So I talked about the beginning of everything, and I was very careful to try and say I'm talking about everything that we can see, everything that we can understand, all of the matter that's out there, the stars, the galaxies, the gas, the dust. But that, in its entirety, only accounts for 4% of the entire universe. Dark matter and dark energy are the other 96%, and they are both still rather a mystery. But that's another story. Thank you for listening.